Okay, then nth roots. What do you think it means when they say nth roots?
To the nth power.
Something to the nth power? And then what is its root? Yeah. It seems complicated, but I think that you have a lot of what it takes already to be able to pretty much work with it. So 7, 6. Pianos. Do you know anything about music? You do. You're not in music though, are you? You two are not in music. Natalie's in music. So, how many keys are in an octave on a piano? Do you know? 8? Including the black ones. Like more than 8, yes. There's 8 white ones, aren't there? Is that how it goes? Or there's 7 white ones? Let's see. There's a picture on page 486. It goes 1, 2, 3, 4, 5, 6, 7. So there's 7 white ones within an octave. So they start you out on middle C, which is like right in the middle of the keyboard. And so you go to C, D, E, F, G, A, B, and then it starts all over again. C is another octave. But in between there's the sharp keys. So you got C sharp and D sharp. There's no E sharp, is there? Which is kind of weird. There isn't. But there's an F sharp and a G sharp and an A sharp. Why isn't there an E sharp? Do you know? Music man?
From E to F is the same as from D to D sharp. It's the same like interval.
Oh, it's the same interval. But it's not a necessary. Yeah, I don't know why they do that. That's kind of weird. There's a reason for it. I'm sure that the guy on the other end knows. And I don't know. But I do know that there's a total of 5 black ones and 7 white ones. And if you put them all together, there's 12. So you go through 12 keys on a keyboard, and then you hit the next octave. And then you go for 12 more. And that's another octave higher than where you start at middle C. And then, I don't know how many octaves there are on a piano. I think it's different depending upon the kind of piano you have. Some keyboards are longer, aren't they? Like grands are bigger than an upright.
Not that way.
No?
But there are some pianos that are just weird.
Like they're longer, they have more octaves that are available. Maybe electronic pianos as well. Okay, so, but nonetheless, Pythagoras, so this goes back a long time, Pythagoras figured out that within an octave that there were equal spacings for the wavelength of sound that comes out of any kind of musical instrument. So they use the piano as an example because we can see the keys. But if you picked up a trombone or a trumpet or a clarinet or a guitar or anything, any musical instrument, it's going to be able to play all 12 of these notes, and then you're going to go to the next octave. So all music is written like this. So if you go from middle C to the next C, and within this, you have 12 steps, and each of those steps is equal. And then this C here has twice, oh gosh, I gotta get the right words here, twice the frequency. This has 2 times the frequency of middle C. And then for every octave as you go, you have twice the frequency again. So if you get to the next C, that's twice the frequency of this. And it's 4 times the frequency of middle C. But if you do this, what you're basically doing is you're breaking up twice the frequency into 12 even steps. So this can be viewed as a geometric series or geometric sequence. Because to go from C to C sharp, and then it goes to D, and then to D sharp, and then it goes to E, and then to F, and then F sharp, and then G, and then G sharp. Is that right? Am I doing this right? And then we go to A sharp, and B. We go to A, we go to A sharp, we go to B, and then we get to C all over again. This is twice the frequency of that. So this is 1/12 greater than this. This is 2/12, 3, 4, 5, 6/12, 7/12, 8/12, 9/12, 10/12, 11/12, and then 12/12. So in order to get this frequency to this frequency, you have to multiply by some value of r, being that it's a geometric sequence. And then to get to the next, we again multiply by r again, and so on and so forth. So in order to go from C all the way to the next octave of C, you have to multiply by r 12 times. So it's r times r times r times r. And you know, this goes all the way across until we get all the way down here. So that's r to the 12th power. So in music, you can, well, you not can, you do, you have to look at frequencies as numerical sequences. And it's a geometric sequence. You're not adding the same amount, you're multiplying by the same amount. So there's a root of this. In this case here, what we're saying is that n is equal to 12. And there's a root to that r to the 12th power. And the root ends up being r. And we find that by taking 1 over r. So for example, if you have x squared, what's the root of x squared? That's equal to x. And what you can do with this is you can say that the root of this, the nth root of this, ends up being 1 over whatever that x squared value is. So in order to find the root of this right here, we want to end up getting r out of this. So what we can do to it is we can multiply by multiply the power by 1/12. And what that's going to give us is it's going to give us the r value, which is the root of r to the 12th. In order to get the root x, which is x to the first power, you may recall that we did things like this. We could multiply that by 1/2 to turn it into the value of 1, and then this ends up being the root of x squared. Another way you can look at that is, what's the root or the square root of x squared? It's going to be x. But here we use a square root symbol. If I had something like x to the third and I took the cubed root of it, that would become x. We've seen that before. And the same thing with this here. If I took x to the third and I multiplied that power by 1/3 by the reciprocal, then you come up with the cubed root also. So we have symbols for x squared, we have symbols for x cubed, for squares and cubes. But after squares and cubes, we don't name the roots any longer. A 4th root is a 4th root. A 12th root is a 12th root. So we don't come up with fancy names like we do in geometry for all of the numbers of sides of different polygons and things. So that's kind of the basic idea of pretty much everything that comes out of this particular lesson, working with roots. Let's see. I'm going to go, fall back on some of this. Middle C has a frequency of 220, I believe. Is that right? Is my memory serve me correctly? Is that what they're saying in there?
Yeah.
Okay, so the frequency of middle C is 220. So then what would,
That's the A below middle C.
oh, is that the A below?
Yeah.
The A below?
The A below,
Not the B below.
not the B below.
It's the A below. Are you sure?
But it says that.
Where are you?
On the first page, side.
In the first paragraph.
Okay, it is common today to tune the A above middle C to 440. So the A above middle C is 440. Okay, so then if we went back down here, and then we have to have A sharp, and then A, so then this is 220. Is that correct? Yes? Okay, so now I've got my numbers in the right place. Okay, so it's not C, that's 220. Okay, so then the idea is that there is an R value that we multiply 220 by once we get A sharp, twice we get B, 3 times we get middle C. And then when we get all the way out here to 13 times, then we get 440.
So not 12 times?
No, it should be, yeah, you're right, it'd be 12 times, but because it's a sequence, it's the way they write this geometric sequence is they take the first term, which if we call it f sub 1, and then they multiply it by the R value to the n minus 1. And in the notation, do they use R? No, they do not. Yes, they use R for that. So in this case here, if we evaluated f sub 1, we would have R to the 0th power. So if this is f sub 1 right here, with R to the 0th power, we could think of this as 220 multiplied R to the 0, or it would be 1 minus 1. So this would just be n minus 1. So this would be a formula for calculating each and every one of these. So then to get from here to here, we have to multiply by R 1 time. So to get to f sub 2, we would then be substituting 2 into here, and this would become R to the 1st power. Therefore, we'd be multiplying by R 1 time. So this would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This would be 13. And if you multiply by R 1 time, and then to get to f sub 3, you would multiply by R a 2nd time. Here you would be a 4th, a 5th, a 6th, a 7th, 8th, 9th, 10th, 11th, 12th. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is multiplying by R 12 times. And that comes from the term number, subtract 1. So that's R to the 12th. Oops, I have to substitute 220 in here. So this would be 220. So that's F sub 13. What would that be?
440.
This would end up being 440, right?
Oh, right.
Okay, good. Are you good with that so far? Are you sure? Taylor? Okay, so now let's take what you just said. So if f sub 13 is 440, Logan, and that's equal to 220 times R to the 13 minus 12, that's the same as saying 440 is equal to 220 times R to the 12th. That's basically what we've said here. So now let's work backwards and figure out what is R. How will you solve this?
Subtract 220.
Subtract 220. Subtract? Divide, because this is multiplication. So you have to divide by 220. So 440 divided by 220 equals, and 2 is equal to R to the 12th. So in other words, to go from 220 to 240, we have to multiply by 2, because the frequency is twice. And there's your 2. So 2 is equal to R to the 12th. So to find out what each and every one of these little r's is, we have to find the 12th root. So how do we find the 12th root of a power of 12? Multiply that by 1/12. And what do we do to this side of the equation to keep it even? Same thing. So we're going to take this to the 1/12th power. So 2 to the 1/12th power is equal to R. Now let's stop here and think about this. If I multiplied 2 to the 12th, so that's this right here, this is 2 to the 12th. If I took that and I multiplied it by itself 12 times, which is, you know, so you're taking 2 to the 12th times 2 to the 12th. I'm not going to write this out 12 times. But if you do this 12 times over, how do we treat the exponents when we're multiplying the same base by itself over and over? What?
You add them?
You add them. So a 12th plus a 12th, 12 times equals 1 whole. So if you do this, you know, and then you do this 12 times, you're going to get 2 to the first, which is what we want. So I'm just verifying by going back and forth with this property. Now, what is that value? It's a little number, isn't it?
It's like 1.06.
Say it again?
1.06.
And it goes on and on and on, doesn't it? Yeah, it's a tough one. So what I have is I have it on Desmos graph. Here's what I have. Let me put this on here for just a moment. You can freeze it and look at it. So what I did is I graphed y to the, or r to the 12th, y equals r to the 12th. So it's a parabola that has a really sharp, steep curve on it. And I also graphed y equals 2. So I'm finding out where 2 is equal to r to the 12th. And then there's going to be two different solutions. 1.059 is what I get, and negative 1.059. But we would throw away the negative, right? And we would use the positive. Unless we wanted to move left, then we can multiply by the negative as well. So that's just a verification in a graphic form of what the 12th root of 2 is equal to.
When you multiply by the reciprocal of that, if you wanted to move to the left?
If you multiplied by, okay, yeah, that's a good point. If you multiplied by 1/12, 2 to the 1/12, you go this direction, right? You gotta do the opposite of multiplying, right? So to go right, we're gonna multiply by 2 to the 12th. To go left, we've gotta divide by 2 to the 12th, which is gonna be the same as multiplying by 1 over 2 to the 12th. Yes, that's correct. I misspoke with the negative. The negative doesn't, the negative's not an answer. Yeah, so if you're gonna do, okay, so how do we do that? We can we can flip the whole thing upside down, right? Using a negative exponent property and get 2 to the negative 1/12. And that's how you would move yourself to the left.
Would it just be 1 over 1.06? You multiply that?
Yeah, it would be. Yeah, it'd be 1 over 1.05. They gave 5.9 on Desmos, but it goes a little further, right? Okay, one note on this, you guys. When you do calculations with this, for example, if I said, you know, what is the frequency of a D? So that's right here. How many times do we have to multiply by R? How many? 5 times. So in this case here, we are going to find, this is f sub 1, 2, 3, 4, 5, 6. Let's see, make some room. If we're going to do f sub 6, that's going to be equal to the 220 multiplied by our R value to the 1, 2, 3, 4, 5, 6. So that's going to be the 5th power. Okay, now, if you took this decimal value out of your calculator and you wrote it down, even if it was 1.059, and you said, well, I'm going to do 220 times 1.059 to the 5th power, you're going to find that you're not going to have an accurate answer. So what you really need to do for accuracy in this case here is use this value. This is exact right here. And you're going to find if you do these homework problems that if you use decimal approximations, your answers may not match what's in the back of the book. So you take this and you say, well, f sub 6 is going to be equal to 220 times 2 to the 1/12th power times 5. So that would end up being 220 times 2 to the 5/12th power. That's f sub 6. And when you do this on the calculator, you're going to have a whole lot more accurate answer than if you stuck in your decimal equivalent. So I'm not sure how much I've said it to you guys, but a rule is this. Whenever you're doing work where you're coming up with approximations like this, you have to keep the value as real as possible, as long through your calculations as you're able to. So in other words, if you're doing some mathematical calculations where you have a root, you don't want to take that decimal equivalent unless it's the very last calculation in the series of steps that you're making. Same thing here. This is a 12th root. So, I mean, we wouldn't do it like this, but if you wrote it in this kind of notation, it would be like this. So this is an exact value when it's written like that. Any calculation that's made beyond that is an estimate. Don't ever do the estimating until it's your very, very last calculation. And then your numbers will be pretty darn accurate. So that's why count back to 7th grade, right? Did I have you for 7th or did Patty? She had you for 7th grade math. Okay, well then go back to 8th grade, at least for me. I was saying repeatedly to not take anything off of the calculator with square roots and things like that. And I tell that to 7th and 8th graders now as well. Don't take off the calculator until it's the very last step that you need. But so many times middle schoolers, they'll look at multiplying roots together and they'll say, well, we'll just take this as a decimal number, this is a decimal number, then they multiply and they get this big old mess on the calculator. And it doesn't even resemble the answer that they're supposed to be getting close to. Let's see. What do you need? I mean, the example number 2 is just taking x to the 5th equals 77 and approximating it to the nearest thousandth. And that's calculator work. Example 3 is using a CAS. Don't worry about that. The first example is the type of thing that we were doing here. So really, if you look at the definition of what an nth root is, we discussed that up here, and that's going to be clean and good to go with. The number of real roots, we're probably okay with this, but the number of real roots, and we kind of looked at some of this back in middle school at one time. If we were to graph, for example, y equals x squared, what's the shape of that going to be? Parabola, yeah. So in this case here, if you drew a horizontal line, that's the number of real solutions. So you have 2. So for any value of y, there are 2 different values of x. If I did y is equal to x cubed, graph something like this. Draw a horizontal line. For that value of y, there's only 1 real solution. Now there's 2 imaginary solutions. And we'll spend a lot more time on that next year, but we're talking about real solutions. In most cases, we keep things real. If you come back to x to the 4th, it's just going to be a tighter parabola. If you have x to the 5th, it's just going to be a steeper S shape to it. So anytime that we have an odd number, we are going to have 1 real solution. Anytime we have an even number, we're going to have 2 real solutions. Keep that in mind.
What do you call the shape that makes when they're 2 and odd?
I don't know. It's an odd function. I don't know. I don't know what that shape is called. But it's an odd function. There's probably a name to it. If you find it, you let me know. But I've never found a use for it other than right now with you asking me. So that's it, I think. I think you ought to be able to do the work.